Okay, good afternoon, everyone. My name is Mii, and I'm the Vice President of the Graduate Student Club in LKC Medicine. So, on behalf of IAS, I would like to give you a warm welcome to the STEM Graduate Colloquium hosted by IAS in collaboration with the GSCs of MAE, MSc, and LKC. So just to give you some background about the IAS, it is an interdisciplinary institute that aims to catalyze high-impact research and inspire a new generation of scientists to become global leaders in science and technology. So today we are extremely honored to have Associate Professor Shweta Agarwala, to give us a talk. And just to give you some brief background about her, she's currently a visiting faculty at MSc in NTU, and back in Denmark, she heads the Printed Electronics and Technology Laboratory, where she focuses on building a biodegradable material library with novel electronic functionalities and using 3D printing for flexible devices with applications in healthcare, wearables, smart textiles, and soft robotics. On top of that, she also serves as a chair of the Women in Engineering Denmark section in the Institute of Electrical and Electronic Engineers. And she is also an advocate for engaging more females in STEM. So without further ado, I welcome Prof Shweta to present today's seminar on making electronics sustainable, solving the dichotomy.
Hello everyone, can you hear me? All the way back? Great. So thanks for the kind introduction. Today I'm going to talk about a problem that we are trying to solve through our research, and I think it's a growing problem in the entire world. Just like plastic waste, we have an issue of sustainability in terms of electronics, how we use electronic materials, how we use electronics as we know of today. And once you are done with that electronics, what happens to that electronics? Where does it go? Is whatever we are doing with our current electronics sustainable? Is it creating issues for us or not? So these are some of the topics that I'm going to discuss moving forward today. Okay, so this is, oh. Super, okay. So before I delve into the technicalities of my presentation, I just want to give you a brief overview where I come from. So I work in Aarhus, which is second largest city in Denmark after Copenhagen. Aarhus University is the second and the oldest research universities in Denmark. So if you are around in the Scandinavian area, please feel free to drop by. It's a beautiful campus, especially in not so much in winters, but really great in summers and autumn season. I work with Department of Electrical and Computer Engineering, and we have a whole range of topics that we are trying to solve problems in, all the way from computer engineering, using machine learning and AI, to basically biomedical engineering as well, and how we can use electronics for different kind of healthcare solutions. I belong to electronics and photonics section, where we are developing new kind of electronics for the next generation to move forward. And you will see some of the snapshots of this research and what we are doing in the presentation later. So if I were to give you a word, electronics, and just ask you to close your eyes for 10 seconds and envision what does this word bring in your images that you have in your brain. I'm pretty sure a lot of you will look at it and think about, processors, hard electronic components like resistors, long dangling wires like cables, right? This all electronics has grown, been made shorter in size. So we now have, when I was young, you haven't seen those days, but the computers used to be like half a room size, right? We worked with like these big screens, and it has to be air-con and special precautions, leave your shoes outdoors and all those things. And now you have basically screens on your watches, and even some rings, smart rings that you have. So that's how electronics has been miniaturized, and it's become more powerful. It has connected people all over the world. So it's basically as we say, the pillar of modern society. But like everything else which has positive sides, everything also has its negative sides. There are problems associated with every solution that you create. So what is the dichotomy or the disconnect that I'm talking about? So we all need electronics. There's no question about that. There's no right or wrong answer here. As a yes is an absolute yes. But if that electronics is creating problems for the future generations, for the planet, for the human health, then we need to stop. We need to think what we are doing, how we are doing, and what needs to change in order to solve this problem that is growing with our hands. Electronic waste is the second largest stream of waste that is growing in the world after plastic. You all are aware of how plastic has created issues. We are now doing, after so many years, waking up and actually doing concrete measures of banning the plastics, which I still see in Singapore, by the way. In Europe, we don't have, even if you pay money, you can't get plastic. You have to carry your own bags. And then you have understood that how you need to be conscious about reusing plastic and all those things. It's the same with electronics. It's only now we are waking up that we have a big growing problem of what we say as electronic waste on our hands. And it's not just about dumping the waste. Okay, if we had enough space on the earth, maybe we can get along with that problem. Okay, let's dump all the electronics. Electronic industry uses some of the most harsh chemicals that you will ever work with. Lead, cadmium, palladium, even some amounts of mercury is used. Now, if you are going to discard your electronics like this in the environment, in the open, rain, temperature, sunshine is going to have an effect on whatever is exposed. Now, once these chemicals start to react, a lot of you will have that basic background that there are a lot of chemical reactions that can take place. Some of these chemical reactions will create byproducts which will be bad for human health. So it's not about just taking space, but a lot of population which is living around these dumps have started to have a lot of health issues. When you look at the data or the amount of electronic waste we are generating, basically you will realize the fact that this electronic waste is starting to increase in the numbers. And these numbers are only correlated to some of the most developed countries in the world. So the shocking thing is that a lot of developing countries and underdeveloped countries are not keeping track of how much electronic waste they are generating. So this staggering number that you see is only because of the developed countries, without excluding or anything that comes with developing countries. And that is shocking because this number would be twice the amount of what we see right now. As I said, it's not just about taking space on Earth. We might have had a lot of space and maybe a lot of things can be absorbed, but it's about the health issues that these things have started to create. Dumps of these, there are now growing reports in WHO where it's almost certain that you cannot leave electronics like that. It needs to be processed in the right way, needs to be recycled or reused in the right way to minimize the growing problem that we have. And the effects of this electronic waste that I'm talking, because we use a lot of harsh chemicals and materials, is there is a lot of release of toxins which are directly affecting the nervous system and even the brains of younger kids which are living around in developing countries around these dumps. So that's one problem. Now let me just shift to some of the people who might be from healthcare or doing something related to medical. We use electronics a lot in healthcare industry, especially when it comes to implantable electronics, which goes inside a human body, right? I mean, this deep brain neurostimulators or pacemakers, it's a very old technology, 5 decades old, right? It's growing strong. But earlier, the lifespan of the human was small, so maybe these things were inside the human body, let's say, for 10 years. But now, as we have better life expectancy, these things can remain inside the human body for a longer time, right? And this creates a problem because this hard electronics that you have, that we put inside the human body, is not compatible with the soft tissues of the humans, right? So when there's such a big mismatch, you have new issues that this electronic creates. So of course, putting these implants will solve some issues, some health issues, that's why they are put there. But for a longer time, after a long time, they create issues like infection, bleeding, perforation, etc. And that is why now the healthcare industry is looking at new generation of electronics which can actually go well with the human cells and tissues. So it has to be soft and flexible like the way we are. So basically the idea is to, looking at the two broad problems that electronics is giving us, is the whole idea is to reshape this electronics. We need to think beyond what we have in new ways so we can redesign this electronics, because when it comes to problems like e-waste, time is running out. The more we sit on it, the more problems are going to creep. And this is exactly what we are doing in our own research. So the idea of our research, the broader vision of our research that I'm going to showcase some of the work is basically reshaping electronics. That's what we call it. What we want to do is to create new materials or devices which are completely biodegradable, which are green. For healthcare, we want to create softer materials or biocompatible materials which are in tune with the human body. And of course, we want to get rid of the extra rigid components like wires and other components to create more flexible kind of devices that can flow. Like the question I would ask you is, why don't you think we should have a cell phone which can be folded like a paper and put in your pocket? Why do you need to carry a squarish, rigid screen all the time and then figure out how to put it in your pockets? Why not, right? So that's the whole idea of creating or going ahead with next generation electronics. So whenever you talk about these kind of solutions which go beyond what is available right now, you would be then thinking of how we can go about it. And the way to go about these things is looking at new electronic materials. So materials which are sourced from environmentally friendly sources, they are abundant, they are sustainable in nature. Then materials which can be completely biodegraded as well, right? Digital processes, meaning the processes that you create. For example, the electronic industry is one of the most infamous industry when it comes to the carbon footprint. We use a lot of water, lot of energy, 24/7, right? Fabs never stop. So they are churning out these components day in and day out. So you need to have processes which are more environmentally friendly with low carbon footprint. So creating new processes. New form factors. Why does the electronic need to be like squarish, hard, rigid? Why can't I have a round screen? Why can't I have a triangular device? Why can't I fold my screens? So these are the factors or form factors that we are talking about. When, for example, if I give you, let's say anything, like imagine a thermometer, for example. If you were to imagine the thermometer, you would think, okay, it's a long rod filled with mercury which will rise in temperature as the temperature rises, or maybe a remote monitoring kind of a thermometer which is a proximity sensor, right? But why can't I have something which is completely printed and acts as a thermometer like a stamp? Possible. And that's where basically is creating new kind of devices and completely new architectures, new structures moving forward. And what we do in our research, basically we are trying to address a bit of each. The majority of my research is based on creating new sustainable materials, because this is the ground up. If you don't have materials, good electronic materials, you cannot create devices. So you need materials, right? And then finally looking at new processes through which you can imagine and process these materials. So the first step in our journey is basically what we call as material innovation. The idea here is creating a library of sustainable materials which are sourced, which are biodegradable, which are biocompatible, and then basically using them for different purposes and applications. I'm not going to go into detail of how these materials and what are the strategies, but I'll just give you a brief overview. So the idea here is basically going back to nature, right? I'll show you some examples. Go back to nature. Nature is full of biodegradable materials, right? But most of these biodegradable materials, unfortunately, are insulating. So they don't have electronic properties. Now this is where basically a lot of chemical engineering, chemistry comes into play. So what we are doing is trying to change the microstructure of these biodegradable materials so that we can infuse different kind of electronic properties in them without compromising on the biodegradability, right? This could be, you want to make a conductor, you want to make a semiconductor, a piezoelectric material, piezoresistive material, so on and so forth. First thing that we made a stop is at trying to create what we call as piezoelectric inks or piezoelectric materials. So PVDF is a well-known piezoelectric material, but the problem is that it's biodegradable, but it has a very small or very low performance. It is low performing material compared to its inorganic or ceramic parts, for example, right? So the idea here was to use a strategy of what we call as fillers. So we used barium titanate, for example, as a filler, and then we kind of retuned the microstructure of the material so it grows in a certain way. So basically it grows in a crystalline form, and that arrangement of crystals basically enhances the piezoelectric properties of the material. So it's a known strategy in material science, and that is basically what we are doing to use. So we basically created a biodegradable PVDF which has slightly better performance than a normal PVDF would have. This is another strategy of using, again, some kind of what we call as a seed material. So the idea here was trying to what you say as fix the chains. So in polymers we have chains, like polymer chains, and you have to open up these chains to have crystallinity in the structure. The more you open up, the more it will be easier for electrons to transport or different kind of electronic properties to come into play. So it's always the case, you want to open up the material. In order to open up, what you do is basically you want to fix them, like provide like nails. You know, you fix a nail, it stops there, you fix another nail and it stops there. So this nail kind of things basically is provided by amine functionalized graphene oxide that we used, which acted as nails to fix the polymer chains. They were aligned, they were opened up, and that basically led to a lot of enhanced properties compared to a normal pristine PVDF that you will find, right? So this is in a very broad term. I won't go into the very basics chemistry of it. Basically what we show, what we have created, as I said, the aim for us is to create a library of new materials. So going back, this is the piezoelectric properties we enhanced, then we went back to the drawing board. Okay, now let's look at the dielectric properties of this material and try to enhance that. Go back to the drawing board and then look at the ferroelectric properties and then trying to enhance that. Because each of these properties can be exploited for different kind of devices. Some will give you good storage devices, energy storage devices. Some will give you good memory devices, so on and so forth. Some will give you good triboelectric generators, because for energy harvesting you need piezoelectric materials. So the idea here is to play with different properties and different strategies. So basically this material that we created is one of the highest reported polymer materials for its piezoelectrical activity, completely biodegradable. So that is basically the achievement of this project that I am just highlighting here. A lot of the piezoelectric materials that you have, just to give you an overview of what piezoelectric material is. Piezoelectric material basically converts the electric field into mechanical force. So electrical energy is converted to mechanical energy and vice versa. So if you apply voltage, you will get some kind of deformation in the material, or if you apply the force, you will get some voltage out of it, right? Most of the polymers, especially available to us, which are biodegradable, they have a big problem that once you make the material, you have to do polling. So polling is a process. What you do is basically when you have the material, even though the material is grown and it has completely crystalline chains, you still have to keep it under a very, very high electric field in order to fix these domains and chains. So that it's fixed, then you remove the electric field and then you get your piezoelectric material. Now this is okay if you are creating regular devices. It really becomes a mess and a threat, I would say, when you have to create biomedical devices or anything to do with healthcare. Because healthcare industry is very conservative. The moment you say, I'm going to use some toxic chemicals, maybe a little bit, but it's toxic, or if you're going to use high voltage, they're simply going to say a big no to you. No, I don't want that device. It uses high electric field, dangerous, toxic material, small amount, still dangerous, right? So the idea of for us, or the challenge for our group was to find a piezoelectric material through which we can create devices, but which does not require what we say as polling, the high electric field. So we went back to nature, and then we started to look what are the biodegradable polymers available in nature, which do not require polling and can be used without high electric field. So this is another project we are working on, which is based on PLLA. It's a completely biodegradable polymer. It's even weaker than PVDF, very, very weak signal. But what we are doing is basically, again, using different strategies. What we are trying to create is this tangled mess of polymer chains that you see, trying to somehow align them, open them up, that's the strategy always, and then fix them in space without electric field so that we can get a higher performance out of these piezoelectric materials. So again, this was basically inspiration by my PhD who did a lot of work, and PLLA in different forms can be found in nature and can be used. So we can draw very great sheets out of it now, which are completely biodegradable and have, I won't say it's the best performance, but I would say it's slightly better than what a normal PLLA would have, or naturally pristine PLLA would have. Then one of my students, she basically looked at what we call as biodegradable substrates. So in electronics, we use a lot of substrates, mostly FR4s, reinforced glass, ITO, that is indium tin oxide, FR4, right? So these are all non-biodegradable substrates. So all your electronics that you are using right now is basically based on a completely non-biodegradable substrate. Now, idea for us to make next kind of healthcare solutions is to find a substrate that can take the mechanical load, but yet be completely biodegradable. So we are looking at different kind of strategies again. So this strategy basically comes from a delicious plate of mussels. I eat meat. So when I was having these mussels, I just got curious sitting with my student, and then we started exploring how mussels come into picture, how they are refined, and how do they end up in restaurant. And we found a very interesting property. Mussels are probably the only organisms on earth that can stick to virtually any surface. Wet, dry, metallic, polymer, you name it, they will stick. And they do so by secreting a protein which is very similar to a hormone found in our bodies. That hormone is dopamine. Whenever you are happy, you're releasing dopamine, right? So that basically gave us a new idea of creating adhesive substrate for a different application, which I'll show later. From this creating dopamine kind of hormone, and then basically using PVA, which is similar to the polymer that is found completely biodegradable. So what we are doing is basically we are mixing a biodegradable polymer PVA with this dopamine adhesive, and then creating what we say as the adhesive substrates. Oh, the video is not playing. Okay, it's never mind. So basically what we can do here is we can tune the addition of this different kind of stamps or substrates depending on where you are sticking. For example, on skin you would need a lower adhesive so you don't have a skin irritation. But if you're sticking the same substrate, let's say on a wood or on a package like a cardboard for smart packaging, right, intelligent packaging, then you would need better adhesion. So we can tune that. So basically this is what we are looking at in this project. Now, what we are doing once you have these materials, the second step, as I said, is to look at processes which can use these materials, but these processes are less energy intensive. They are more friendly to the environment. And this is where basically whole printed electronics come into picture. So the idea of printed electronics is that it uses less energy, because printers by far, especially if the smaller they are going to use less energy. They are also going to use what we say as less material, because the inks that we use are much smaller in quantity as against working on a wafer, which comes from these long ingots. And then we can also use what we say as new materials, which is not possible with the current manufacturing of electronics, because we use high temperatures and high pressure systems, vacuum systems. All these biodegradable materials are going to vanish if you are to create new kind of electronics. So if you look at the conventional way of creating electronic versus the new way of creating printed electronics, you will see that conventional way is basically, as I said, you start from all the way from sand. So some of you who have the electronics background would know that you basically take sand, not any sand, but a certain crystalline structure of sand, basically create these ingots, cut them, and then create these wafers, and from these wafers you grow your electronics, or you basically deposit your electronics. So it's a multi-step, highly energy inefficient process. Whereas when it comes to printing electronics, all you have to do is make an ink and then use it into a printer, and just like you print on your paper, you have a circuit printed in a 2D format on it. So there are many advantages of using printed electronics as versus using conventional methods. I'm not here advocating that, or saying that we have to replace the entire electronic industry and we don't have to work with silicon or germanium or the wafers or gallium arsenide anymore. No, but the fact that we can complement existing electronics with something more which can help us work with new materials and new ways is what basically I'm trying to say here. So what we are doing as a portfolio in our lab is basically creating and putting electronics, as I like to say, where it doesn't belong. Electronics you might not have seen on a wood or on a chair or on a wall, but this is where we want to put electronics. Why can't electronics goes on surfaces which we interact with every day? Why do you need to carry your keyboard? Why can't you have a solution which will project letters or something on from your skin all the way to the wall and have a screen? These kind of solutions we are trying to develop to see where we can go and how far we can go. But so far, we have taken tiny baby steps in terms of creating different kind of sensors and some variables and antennas and transistors on different kind of surfaces, as you can see here. Some of them are flexible, some of them are stretchable, some of them are bendable, so and so forth. And I'll give you some examples of what we are doing moving forward. But just to give you a brief overview of what printing electronic entails, it basically is exactly the same as you are printing on paper. You create a design file. In this case, the design file, of course, is a circuit. So depending whether you're creating a heater or you are creating a transistor, your design will be different. Now you have the standard printer. Of course, the printers that we use are only slight modification of the inkjet printers sitting in your laboratories or in your offices. But what we do here is just imagine the same kind of inkjet printer, but replace the colored inks with a functional ink. Now this functional ink properties of the circuit will come from these functional inks. So whether it's a semiconductor, so you will use a semiconducting ink, a conducting ink, or an insulating ink. And then finally you print on whatever your substrate of choice is. This could be plastic, it could be paper, it could be wood, it could be textile, anything. And then at the end what you get is a printed product. Of course you have to do some kind of post-processing after that. The other ways in which you can create the next generation electronics, I'll just give you a very brief of what basically is going around in the industries. One of them is what we call as structural electronics, meaning to say that you have, I'm pretty sure a lot of you have wetted your hands in 3D printers at some point. So you print what we say as a 3D printed part, then you design your file to leave the gaps or the holes, voids for your electronics. You put your electronics and then you continue to build the part. So basically the electronics is completely embedded inside the electronics, the printed part, and that basically leads to a structural electronics because you don't have an exposed electronics per se. And that has basically made a lot of, this is of special interest for example, aerospace or drones where you don't want whole electronics to be exposed but rather be structurally embedded. In-mold electronics is basically the idea of putting electronics on what we say are passive surfaces. For example, the middle image here, it's a sole of a shoe. You never put electronics in a sole of a shoe. It's a passive thing, right? If you wear your shoes, you have sole, that's fine. But basically, if I were to put an electronics there, what will happen? So this is basically a product, I think it's Nike or Reebok, which is coming up with this, what they call as special shoe for diabetic patients. So using this electronics which is embedded inside and molded inside the sole, what they are doing is they are trying to create or measure the pressure of diabetic patients because they have different pressure in their 2 feet. And once you create you map out that pressure, then the doctors can provide them ways in which they can correct that pressure. Similarly, for your cars and automobiles, in-mold electronics is huge because you don't want any hard, knobs or switches in your cars anymore. You want everything to be seamless on a dashboard or let's say in your seats and textiles. So that is basically where in-mold electronics comes into picture. And then we have what we say as hybrid electronics, which is the current standard or where the industry is moving. Basically, it's a game sum or combination of hard, rigid electronics off the shelf you can buy, so different microprocessors, LEDs, but a lot of the parts are printed. So you can print interconnects, you can print basic resistors, you can print capacitors, you can print LEDs now, so that is all possible. So it's basically a combination. So you have the flexibility that comes, but with small areas where you have still off-the-shelf components to create these small miniaturized semi-flexible devices. So printed electronics has basically enabled a whole era of new kind of devices, and some of the applications I've tried to show here. So smart packaging is one, and smart packaging is not just for decoration purposes, but the idea here is, let's say you buy a medicine. There is a barcode, the packaging is there, and then once you scan it using your phone, you should be able to have all the information. The packaging should give you all the information, when you should take the medicine, when it will expire, so on and so forth. Another important application of smart packaging is, I think it's Samsung, which is now doing R&D in the fact that they are creating a new kind of refrigerator, which will come with its own boxes to store the food. Now these boxes will have printed electronics around them to pick up, they will have sensors, biosensors basically, to pick up whether your food has gone bad or not. So let's say you put rice, you make rice, you put it in the box, put it inside the fridge. Now after 2 days you see that the strip of the box has turned red. Basically it's an indication to show that you cannot eat that rice anymore. It's gone bad, so throw it off. Of course it's not applicable to everything that you put, but there are few applications of food that they are trying to target, which are commonly used. Flexible screens, smart clothings, basically these are applications that are trying to take forward. So the idea here is connecting the rigid components that you already have, that we already use, to flexible substrates. So you just use the substrate as flexible and then put your components, or you basically have flexible components, that is completely printed components, and then on the flexible substrates. So this is the where the design is. Now, to take you forward, that basically we talked about printing processes, we talked about different materials, but what are we doing with it? What kind of solutions are we creating? So of course everything is biodegradable and the processes are less energy intensive, but then basically I'm an engineer, I like to solve problems. So we try to target specific problems in order to put whatever we create in our lab moving forward. But before I delve into those, I just want you all to remember 3 basic terms. One term is biodegradable. Anything biodegradable is basically capable of completely being decomposed, right? So when we talk about biodegradability, something that can be degraded, whether it's in water environment, soil, or any other environment. Biocompatibility is a term which refers to anything which is not harmful for humans or any living organisms. So a biodegradable material might not necessarily be biocompatible. Biocompatible is something that is safe to put on your body. The last term that I want you to remember is bioresorbable. Bioresorbable materials are materials which when you put inside the body, implant inside the human body, after a while they are going to be either released from your body without any byproducts, or they are going to degrade without releasing any toxins. So that means the degradation happens inside the human body, right? So what we are doing here is creating these kind of solutions. So for all the materials that we have in the lab and the processes, basically this is a problem that is common all over the world. So the scenario here is when a person is admitted to ICU, that is intensive care unit, basically they are suffering from disease, right, and a severe disease, that's why they are in ICU. And they are mostly immobile in ICU, that they are lying in bed at least for a week or so. Now when you do that, even a healthy person, forget about an ill person, you will start to lose your muscle mass. Whatever muscles you have developed, you will have as high as 50% of muscle loss in the first 5 days. It's as bad as that. If you are young and healthy, maybe you will survive. But if we are talking about elderly population, some of the deaths happen not because of the disease, but because there's no muscle mass left for the person to survive. So it's a really severe problem. So the idea here, the way it is treated, at least in Scandinavia or I think all over the world, is basically when somebody is discharged from the hospital, they have to go to a specialist care. And if you have ever gone for your health checkup, you know they will put these big bulky electrodes all over your body with a gel solution, and then they will start to stimulate your muscles. But by then it's already too late. You have lost a lot of muscle mass. It's very difficult to build the muscles. it's easy to preserve the muscles rather than build the muscles, right? So basically what we did here was we had a lot of biocompatible, bioresorbable materials in the lab. So we created a 3 electrode system on an e-textile. So this is a compressive stocking that the patient is wearing. Compressive stockings are kind of mandatory for all patients in Scandinavia to wear because it keeps the muscles intact. So you don't kind of suppresses your muscles to reduce the muscle wastage or muscle atrophy. And then we printed all the 3 electrode systems with printed electronics on them, connected using a wire to a small stimulator. The stimulator is also built in-house, where you have the right frequency to stimulate depending on the muscle we are targeting. In this case, we are targeting what we say as the thigh muscles, right? Once you stimulate them, basically we did a lot of clinical trials, and we saw that stimulating these muscles twice a day from day 1 of the ICU patient, you can stop this muscle wastage. Right. So this is basically what we have done. We started this project in 2019. We did a lot of trials. We created like 500 to 700 stockings in our own lab at a mini manufacturing unit that we developed. And we did trials on COVID-19 patients. Then right now we concluded our studies on Bispebjerg Hospital in Copenhagen on different kind of ICU patients. And that is a stage 1. Now we are on stage 2. So you see these big, long, dangling wires. So the stage 2 or the prototype 2 that we are developing is basically to replace these wires to have just like a designer stocking for you to wear in ICU, right? And that will stimulate your muscles and will help you in stopping, help someone to stopping the muscle wastage that could be life-threatening. So this is one example of how the materials and processes come together to create a solution or a treatment for something that could be life-threatening. We also do a lot of work around biomedical devices, so my focus has been biomedical and healthcare. The idea here is to create different kind of wearable devices for different applications. For example, elderly people have difficulty swallowing the food after a certain age. So we are trying to understand the pressure on the throat and then basically give advice to the doctors that what is the pressure, how much the pressure is lesser, so and so forth, so they can come up with new solutions. Same goes for different applications of joints and providing rehabilitation for joints and different organs. Another application is what we do is in wound management. So wound management is an area which is very rudimentary, meaning it has not seen innovation in the last 5 decades. How do you inspect a wound, no matter if it's acute or chronic wound? You always have to open the bandage. The doctor always has to inspect it in order to see how the wound is doing. There's no other way, right? Now this is okay if you are young and healthy and have acute wounds because they heal very well with time. Diabetic patients, patients with high blood pressure, their wounds can take up to a year to heal, and it can be really, really painful for them. So dressing and looking at the wound just for the sake of looking is not a good solution. It is very troublesome and very painful for these patients. So the idea here is how can we create new wound management systems? What can electronics or other materials engineers do to create these solutions? So what we do is we are creating what we call as on-skin patches to monitor the wounds. When a wound is healing itself, there are a lot of changes that happen in the wound. pH, temperature, oxygen level, they all change with time. If you can monitor which way the change is happening, it will give an indication to the doctors whether the wounds are healing in the right direction or the wrong direction. And then you can create your solutions or you can prescribe the medicines accordingly. This is also bioresorbable patches again for wound management. So when you get a bruise, what do? Run to the nearest pharmacy, get a plaster, put it on your bruise, right? This is what you do. What is that plaster? What does that plaster contain? Plastic, but what is inside the plastic? If I put a normal plastic, it won't heal your wound, right? What? Cotton? Cotton will not heal the wound. It's just yeah, it has an antiseptic medicine. So it's a drug basically. It's a chemical formula that you put on your bruise, and that antiseptic cream will, basically it does not heal your wound. What it does, it stops the bacteria to be coming inside your wound, and it helps in the regeneration of the skin. So you heal yourself. There's nothing in this entire medicine that heals you. Basically, these are only tools for your body to help you to heal, right? Your body heals itself. Now, there is a growing consensus in healthcare industry that when you have a bruise, if you have some kind of little electric stimulation at the wounds or some kind of a heat signature, I'm not talking about a big jump in the heat. Our body is maintained as 37 degrees. So maybe 37.1, 37.2. If you have a small heat signature, that will tend to heal the wounds faster. So I work with doctors a lot. So the doctor basically told me, okay, can we, Shweta, create a stamp or a patch which can increase the temperature at the wound site or provide some electric stimulation, as you can see, using this interdigitated circuit at the wounds. So basically we looked at, again, hydrogels, which are tissue engineering materials, 90% water, completely biocompatible, so very good for skin. Then we made what we say as in-house inks, which are completely biocompatible, good for human skin, printed them, created a sandwich structure, one with interdigitated electrodes, the other with a microheater, and then we basically looked into it, whether it's compatible with human skin, is the ink leaking out, what happens to the wounds, so on and so forth. So this is an ongoing study where we are trying to look how it would help in the wound management or closing of the wounds, basically. Another concern with doctors is that it's very routine now for at the older age to have knee implant, hip implant, right? There are a lot of implants happening. Now, when the implant is done, the implant is basically titanium metal, right? You implant, put it there. The operation is done, the patient goes back to the house. Now, there's only a 50% chance that the implant will be accepted by the human body. No matter how well you are prepared, how much studies you do, how well you design the implant. So what happens is that once the patient starts to experience, let's say, pain, bleeding, or any other issues, then they come back to the doctors and say, okay, my implant, there seems to be something wrong, and then the investigations basically are opened up. So doctors basically want a solution where something goes with the implant, let's say electronics, a sensor, which can pick up the signals from the body and tell the doctors, okay, the implant is being accepted, not accepted, something going wrong. But then after the implant is accepted by the body, you don't need that electronics there, right? The implant should be a pure implant. Then basically the idea here is to have resorbable electronics. Once it has done its job, it should basically be either released by the body or it should degrade on its own by the body, right? And that was basically a proof of concept or where we wanted to use a biocompatible, bioresorbable substrate, put electronics, print electronics, which is basically a basic antenna, and then so we basically keep this whole system for 2 to 3 months in the same environment as inside the human body. And within 3 months' time, you will see that after it's done its job, it gives you signals in the range that we want. There's nothing left completely. The ink is gone, the substrate is gone without leaving any bioproducts or toxic products outside. So basically, this is the idea moving forward that your implants, some implants might have electronics going inside the human body, which will degrade. Last, I would want to just say that in healthcare, especially when you talk about small biomedical devices, we use a lot of wires, and a lot of work in printed electronics has been concentrated on creating interconnects, creating electrodes, right? Which is great, but in electronics, if you were to replace your entire laptop or your entire phones with printed electronics, you would have to replace wires at some point, right? So in this project, basically what we are looking at is looking at different kind of wires, cables, coaxial cables, shielding cables, low frequency, high frequency that we use in electronics, and then trying to print them. And this is what I meant initially when I said there's a change in the form factor. So if I give you, okay, this is the coaxial cable, it looks something like this on the left-hand side. But when I start printing it, of course this is a very crude design because we just started the study, it looks nothing like a wire. It's like you have printed some 2-3 lines on a piece of paper. But let me tell you, trust me, it works very well just like a coaxial cable. So this is what I mean by changing the form factor. Moving forward, maybe the devices that you work, cables that you work will not look like the way they look like right now. Their form factor or their shape, structure and architecture will be completely changed, right? So Coming back to the question that I started this conversation with is e-waste problem of sustainability in electronics. Basically the way we are trying, there are different ways of trying to tackle this problem. Reusing the electronics, recycling the electronic components, and the way we are doing is basically ground up. We are trying to create new solutions which can be sustained for a longer time, which can be completely degraded on the earth, so they don't leave any toxins. But what can you do basically to help in going forward to maintaining the sustainability or enhancing the sustainability in electronics is buy only what you need. Don't wait for the next iPhone when your current iPhone is working well. Don't go and rush to the market, right? Repair instead of replace. Well, this is, at least the European Union has made it very clear that they want to ask manufacturers to start collecting back the unused products so that they can be recycled at the manufacturing unit now. I don't know what is the scenario in Singapore right now. Donate your usable items. If you have friends or kids in your house, give them the products that you don't use right now. Recycle, I think Singapore has started some work in that. You do have recycling facilities at designated places where you can recycle your electronics. Of course, the whole recycling of electronics is another topic that I can talk about for another 1 hour, because the recycling that we have in place for electronics is completely ineffective and insufficient to deal with the problem. We don't recycle electronics the way we should be doing it. But that's for another day. And create awareness. A lot of people don't think there is a problem of e-waste. A lot of people that I meet, they say, no, there's no problem. We don't see the heaps of these electronic waste that you keep talking about. Well, because we are a developed country, we don't see it ourselves. It's all being dumped in a developing country, and people are dealing with those issues. So create and talk about these things so that people know and they're aware about these issues, that we have a growing problem at our hands. So lastly, I'd just like to thank my group, who are the force behind the awesome work that we do. They are passionate about the work and the vision, and they are really into it for a reason. And last, I would like to leave you all with just a question, that all of you are from different disciplines, and in your own ways, you are creating different solutions for sustainability, whether it's smart aviation, climate change solutions, renewable energy, or smart manufacturing. But any solution that you create, no matter for what, will use electronics. You cannot go without it. And if that electronics itself is not sustainable, can you really say that your solution is 100% sustainable? Thank you.
Hello. Yeah. If there are any questions, you can raise your hand. Okay, so I'll start with the first question. So there's actually a question from the registration. So they asked, you mentioned a lot about biodegradability and all that, and even at the end you were mentioning that the recycling in current waste treatment process is not sufficient. Maybe you can actually share a bit on this, like what exactly is the current waste treatment process of this e-waste?
Yeah, so currently, at least I don't know about Singapore, but in Europe, the way it is done, and I think it's a standard in US and Europe. So let's say you want to recycle your, so there are only one category of criteria to segregate the electronics that you collect. One is whether it has a battery or it does not have a battery. If it uses a battery, then it goes in one slot. If it does not have a battery, like washing machine or refrigerator, then it goes into another slot. Now, the ones which have battery, they are also processed in the same way without the battery. What they will do is basically shred, like the way we shred all the electronics. Put it inside a shredder and go. Now, you cannot do that, because in a battery itself, we have 3 or 4 different kind of materials. A hand phone is very different from a solar cell. A solar cell is very different from other electronics. So you have to segregate them according to their function and the materials specifically they are using. Try to extract those materials if we can reuse them back, but that is not happening at all. And the way it is being done is in a very crude way, that we just have shown that we have shredded and then we have off our hands. But that's not the way it should be. Yeah.
Thank you. Are there any questions? Actually, I have another one. Oh, okay.
That's not the way it should be.
Sorry, can you repeat your question?
So ideally, what do you think the process should be to recycle it?
Well, if I had that answer, I would be a multimillionaire by now. But no. Well, I think first of all, we need to start segregating, as I said, according to the materials and start reusing what we have already put. A lot of silver, anything that is electronics uses huge amount of silver. Anything that you touch has a silver-based electrode system there. So there's a lot of silver. Silver is in scarcity right now. It's considered one of the rare materials because we don't have enough silver to replace and make future devices. Why can't we start collecting the ones that we have already made from them? We don't do that anymore. So that is the way of rethinking the solutions, what we have collected, start to reuse it. The other way of recycling is we are talking about AI machine learning. We have new models that we can do intelligent solutions with. Why can't you put AI and machine learning to use and have these recycling solutions so the devices can be segregated. Robotic arms, why can't we have robotic systems in place that can start to remove the batteries, scrape the materials? It can be done, but it's not being done because it's a big investment of money. There needs to be legislation and things that needs to come into place. So yeah, it takes time.
Question about the stocking where you were mentioning about reducing muscle loss. So I saw that in the photo your studies were on the legs. So when you're measuring the muscle loss, was it just on the legs or like does the stimulation at the legs also help with muscle loss throughout?
No, it's very targeted. So we are it's not on the full leg. So we are only targeting 2 muscles on the thighs right now. That's the only thing. So it doesn't do anything for the lower leg. But that is basically the first start. So of course, if you have to, because of course the muscle loss when it happens all over the body. It doesn't happen, right? So ideal would be to create a suit, with muscle stimulator and wear it for the patient. But that's not possible. So we are only doing bit by bit for now. Yeah.
Thank you.